Getting back to maths, which is what it's all about, really. And it's a great pleasure to introduce Bodil Branner to give the last talk, and it's a particular pleasure for me. Bodil happens to be in my research area, so I was absolutely delighted when Caroline said that Bodil was on the committee and would be here. And I've met Bodil at conferences over the years in complex dynamics, and it's always been a huge pleasure. And actually, there are I think quite a lot of women in our area, and I think partly that probably is due to Bodil kind of being an inspirational figure. And it's a very fun area to be in, and it's kind of, and Bodil's an excellent speaker, and it's been lovely to have her here, and I'm very pleased that she's finishing the conference while speaking.
Thank you very much. So I want to start by thanking Gwyneth and Ben for making it possible for us to have our meeting of the EMS committee here and to join you. I'm sorry not to have been to the talks, but that's how it goes. And also thank you, Gwyneth, for inviting me to speak. I got the invitation when I was on one of my intensive weeks of working in Barcelona. And you asked me to say something about myself. So I'll do that. And you heard part of it yesterday, but you may have wondered also, how did I ever ended up on being on a panel before the International Congress? So I'll tell you about that also. But the thing was that I have been now retired for 2 years, and almost every other month I'm going to Barcelona for 1 week, and I work on mathematics day and night. And it just seems, to some people it seems very odd. Why are you doing that? And are you paid for it? No. And so I can't stop doing that. And what I'm really working on, I'm working on a book together with a wonderful woman in Barcelona. So somehow we're laughing that I'm trying to understand all the tools I've been using for the last 30 years without really understanding them, because I was just told that they worked and I was using them, and writing a book, you really have to know what you're doing. So that's why I, on my way back in the airplane, thought the title could be Why I Continue to Be Fascinated by Mathematics. So the book is about surgery in holomorphic dynamics. So I'll tell you how I get to work in holomorphic dynamics and what it is. Not so much about what kind of questions we ask and what kind of answers we get. You'll see some examples, but maybe I should say also about my background, that my master thesis was in algebraic topology. And then when I moved to the technical university, it was not so popular if I would continue to work in algebraic topology, but my background is really in topology. So I moved gradually to differential geometry and dynamical systems. So what is holomorphic dynamics? So I'm interested in the part where you iterate holomorphic maps. So you should think of, you have a map which is holomorphic, so differentiable in the complex variable from one space to the same space, so that you are able to iterate infinitely often. So you take an arbitrary starting point from the space, then you apply the function, you get a new point, and you apply the function again and again, and we say that you have an orbit. And the simplest interesting examples when doing these kind of things, that's quadratic polynomials. So a quadratic polynomial is a very simple function, and many people are just looking at one of the form z squared plus a complex variable. So you can show that that's enough. If you understand polynomials in this form, you understand all polynomials, because you can change your coordinates so that you get them into this form. So C is a parameter, so we are looking at a one-parameter family of holomorphic mappings. So how did I get to work on holomorphic dynamics? As I would say, almost everything else in my life, it was just by chance. And so moving into dynamical systems, I was to advise a student who was to do a master thesis, and we were looking at different kinds of dynamical systems. First, some systems of differential equations, and we happened to stumble over, it's not mentioned here, but a paper by Robert May in Nature about chaos, where he was iterating and doing a lot of numerical studies for iterating real quadratic polynomials as a model for population. I mean, one generation to become the next generation, and so on. And so my student, there was one sentence in the paper saying it would be very interesting if somebody would look at cubic polynomials. So I said to the student, so you look at cubic polynomials. So he did a lot of similar numerical calculations, and I was deeply fascinated by that. So I kept working on iteration of real cubic polynomials. And then in 1983, the physicists at the Niels Bohr Institute were having a workshop on chaos, and they advertised it widely. Of course, they were mainly physicists, but they were all kinds of natural scientists. And two mathematicians came, and that was a French mathematician, Adrien Douady, and the American mathematician, John Hubbard, who were at the time pioneering what was going on when you were iterating quadratic polynomials in the complex. So I just met them by chance, I would say. I was called by the physicists saying, please, could you take care of these two mathematicians coming? And at the end, it's not clear who took care of whom, because they said, you should really go to the complex. I mean, every polynomial has a natural extension to the complex plane. And in the complex, there are so many stronger tools available, and it's really true. In the real polynomial situation, you were dividing things into different cases, and here it's just you look at it in one. So we often say, to make it easier, make it complex. And this is true. So what's next? So I should say, before I say something here, you may, if you were paying attention to the years, you would see I met them in 1983. That was before the panel at the Berkeley International Congress in '86. So what happened was that in the year after, I was to be a visiting professor at Cornell University, where Hubbard was. And the first guest in my house there, I went with my husband and two children, were Linda Keene, who is also working in holomorphic dynamics, among other things. And at the moment, she was the president of AWM. So this is the Association for Women in Mathematics. So that's how I knew her, and she knew me, and that's how I got invited to the panel, by chance. So as I told you, I'm working together with Nuria Fagea at the University of Barcelona, and it takes a long time to write a book. So it's a book about surgery in holomorphic dynamics. We have worked together for a long time and had the plan about a book, and it wasn't going to happen because she has 4 children, and I was so busy with lots of things, and that was part of why I retired. I said, if this is ever going to be, I have to get rid of something. So I got rid of the teaching, although I like teaching. So I'm the one to travel, because the traveling she is doing, that's to go to conferences. It's always a big effort with 4 children. So I have the same kind of satisfaction of doing it, and I have the same kick of when everything falls into place, and you know, it's hard work and it's always painful, but then suddenly, wow. So now it will be more mathematics. Here's one very particular, no, I want to say one thing more. So there are many groups in different areas of mathematics, also in holomorphic dynamics. So I happened to become a member of the big group around Adrien Douady. And he died some years ago. He was a very special person, and he was saying, never hide anything, always discuss your ideas, be open. And I really felt very happy in this environment. There are other groups I know where it's so competitive, and you're hiding and you're not discussing anything because, ooh, somebody could steal your ideas or I don't know what. And I mean, I think that's part of why there are so many women in that group. Anyway, so here is, oops, sorry, that's not what I meant. So you see, this is called the Douady rabbit. That was his favorite example of what could happen. So we take a particular c value for this quadratic polynomial, and it's chosen so that when we look at 0 and take the orbit, so put 0 in here, the first iterate will give you c, the next iterate will give you c squared plus c, and the next again will give you that squared plus c, and you are asking that it comes back to 0. So 0 is periodic of period 3. So here's 0, here's c, here's the next iterate, and then you're going back to 0. Wow, I'm shaking. So 0 is not just an arbitrary point. 0 is the only point in the plane. There's a derivative missing here, where the derivative of 0 is 0. No, where the derivative is 0. It's a critical point. It's a special point. And it turns out that if we know the behavior of the critical point, we kind of know the global behavior of what's going on. So just these pictures were made with colors, were made in the early 80s. And so kind of the mathematical understanding came before the colorful pictures, but they are illustrating what's going on. So a black point means that if you start with a set value, which is colored black eventually, that's because the orbit stays bounded. The more colorful thing out here, you iterate and you go off towards infinity, and that's kind of measuring how fast or how slow you go off. So the colors is measuring that. And then this is the boundary of what you see. So this is called the Julia set in English, after the French mathematician Julia. So that's the common boundary of the black points and the more colorful points. And so as you can see, they have distinguished dynamical behavior because black points have bounded orbits and more colorful points have unbounded orbits. They're going off to infinity. But there is a different way of coloring this. So we take the same c value. We remember that 0 is periodic of period 3. I don't know if you can see that 0 is now marked here. C here, c squared plus c. And in fact, that orbit is attracting. So all the points which were marked black before, at least in the interior of things, are eventually being attracted to the periodic orbit of period 3. So if we only look at every third iterate, then a point will be attracted either to 0, to c, or to c squared plus c, or going off to infinity. And we can color them according to what is happening. So everything in here is, if you take, so So let me first say, a blue point here goes up to the red points here, then to the green points, and then they come back. So every third iterate will eventually make it tend to 0. A green point here goes first here, then there, then there. And then when you do it every third time, you're always coming back to the green. I hope you understand the coloring. So what we can see from the example is that it's a complicated dynamics, and there is a theorem saying that the Julia set, which is a fractal, no, that's not where I should say. So the Julia set, where is it set? It's not set. Okay, it's not set. So I'll say it in words. The Julia set is the common boundary of blue points, of red points, of green points, of white points. So it means whichever point I look at here, I can make a sequence of blue points converging to it. I can make a sequence of red points converging to it. I can make a sequence of green points converging to it, or a white points converging to it. The white points is not so strange, I mean, coming from outside. So the geometry is very complicated. And the dynamics on this Julia set is what's called chaotic, and what it really means is sensitivity on initial condition, which is not so strange if you first get to believe in this coloring, because if I push a little bit to a point here, I may move into a blue area, or a red, or a green, or a white, and I have completely different behavior. So there is sensitivity on where I start. So the Julia set can be very different. And what we really want to do is to classify them in the sense that we want to divide the parameter plane, the C-plane, into maximal domains where the corresponding polynomial will have qualitatively the same dynamical behavior. So what does that mean? Okay, no, this was a wishful. That's our goal. So here's the first rough division. I'll come back to what it means with this qualitative dynamical behavior. So when you look at all these drawings, and you can prove it, then you see roughly they come in two species. Some of them are connected, and then there are disconnected things. And for the quadratic polynomials, if they are disconnected, they are always totally disconnected, and that means it's a Cantor set. So growing up with topology, I'd learned about all these rare, peculiar things like Cantor sets or whatever, and Cantor set was invented to understand what should I say? Infinity. I mean, Cantor was saying there are uncountably sets. Well, no, I can't say that. There are two kinds of infinity. No matter. I don't want to get into this. But then suddenly here, they are common features. So everything I'd ever learned about in topology are staring at me either in the Julia sets or in parameter space as something that shows up. So if we just decide, okay, we're going to divide the C-plane into the part where the Julia set is connected and the part where it's disconnected. That's a very rough distinction of we have different dynamical behavior. And the result is that what is now colored black, that's where we have connected Julia set. And what is now colored in, so I'm in the C-plane. I'm not at dynamical planes, I'm in the parameter space. So what's colorful correspond to Cantor sets dynamically. So the definition of the Mandelbrot set is that that's the C values where the Julia set is connected. So that seems to be a complicated thing to measure. First you have to take a C value, then you have to find the Julia set, then you have to decide if it's connected or not. So that's seems hopeless, but it's not, because there is a fantastic theorem behind that. If C is such that the Julia set is connected, it's if and only if the orbit of the critical point, remember that was 0, under iteration is contained in the disk of radius 2. So you just ask your computer to do, say, 1,000 or more iterations and see if you stay in the disk of radius 2, and if so, you mark the point black. So that's just interesting that you can do that. And then it's kind of a miracle that doing so will answer the question we asked. We want to classify domains in the C-plane where we have the dynamically the same qualitative behavior. And what's doing that for us is the boundary of the Mandelbrot set, not the Mandelbrot set itself, but the boundary. So when we remove the boundary from the plane, it falls into infinitely many connected components. I mean, here's one in the middle, and one here, and one. You just see all these white things. So there are uncountably many. There are countably many of those, but infinitely many. So we say that this is a bifurcation set. So what I'm going to illustrate for you is whenever we are inside one of the connected components, we have qualitatively the same dynamics. When we move from one component to another, we change the dynamics. So as an example, here's one of these connected components. So this picture up here is the Julia set of the C value from here, and this down here is the Julia set from here. Then there are just two others. This is outside the Mandelbrot set, so you see this is disconnected. This is close by, so it looks a bit like it, but it's different. So what it means that they have qualitatively the same dynamics is that you take the two different polynomials and you say they have qualitatively the same dynamics if you can find a homeomorphism from the plane to the plane so that this diagram becomes commutative. Because then dynamics here, an orbit up here, will be mapped to an orbit down here. And how do we prove such a thing? We prove it by using surgery. So up till now I've not talked anything about surgery. So we like to think about that there are three types of surgery, although they may not all deserve to be called surgery. So the first one is that we keep the space, we keep the map, but we change the complex structure. I'm going to tell you what that means. Next thing, we keep the space, but we change the map and we change the complex structure. Third thing, which is a real surgery, is we change the space, the map, and the complex structure, and the way we change the space is that we cut it. Maybe we remove some part and we paste things together or sew or whatever you want to say in surgery. So what is the purpose? We want to construct new maps with prescribed dynamics or to understand dynamics better. And we want to obtain results about the structure in parameter space. And Duardy's motto was that we plow in the dynamical plane. So we do all the work in the dynamical planes, and then we harvest in parameter space. So the essential tools are that we work with quasi-conformal mappings. We work with almost complex structures, and there is a fantastic theorem, the measurable Riemann mapping theorem, which will do a lot of the work for us. So what does it mean that we have a quasi-conformal mapping? I'm not going into all the details. So it's an orientation preserving, should be a homeomorphism, I should say, homeomorphism here, which is differentiable in the real sense almost everywhere, and then technical thing, absolutely continuous. So if you look at a point where it's differentiable, that means that you have a linear map from the tangent space at the point set. This is just a copy of the complex plane to the tangent space at the image point. So that's also just a tangent plane, C. So we can define an ellipse in the tangent space you come from by saying this should be the ellipse which is mapped to the unit circle. Clearly, in general, it's an ellipse, and it could be a circle, but that's very special. So in general, we will obtain a field of ellipses. If we have a quasi-conformal mapping, we'll obtain the field of ellipses in the space almost everywhere. An almost complex structure can be explained geometrically by saying, where is this? That at almost every point you do have an ellipse. Now, it may be a little bit technical to say this can give you a complex structure. Can I do that? If I have a plane, this is just, and I have a vector, and our standard complex structure is I should be able to tell you how do I multiply by I, how do I make it into a complex vector space. I should be able to multiply the vector by complex number, and that's the same thing as saying, in that sense, I know how to multiply a vector by a real number, so what it really remains to tell is how to multiply by I, and you all know what you do. You just turn the vector 90 degrees in the direction. And when you do it twice, you get to minus v. So and you can then say, if you have given an ellipse, that will define you a complex structure in the vector space. So suppose you have a vector ending on this ellipse. What should it be to multiply by I? You should find what's called the conjugate diameter, which is really taking all the midpoints of these parallel lines. So let me put a star here. This is my new definition of what it means to say I times the vector. Because if you do it again, you will come to this opposite thing. So that's really just an ordinary multiplication. So it's obeying all the rules. So giving this field of ellipses is just giving you a complex structure in almost all tangent spaces. And I always feel like my view is such that if I take off my glasses, everything is distorted. So I could think of having some glasses made that I would see all of these ellipses to the left as circles. And you would think that's the ordinary complex structure. Because in the circle, these conjugate diameters is really think you go half it's really always, you take a diameter and you go perpendicular to that, that's the conjugate. So we have a measure for the distortion, which is also called the dilatation. So you say it's the major axis divided by the minor axis. So if it's very long and very thin, you get a big number for the distortion. If it's a circle, it's just 1. So it's a measure for how far away you are from your ordinary complex structure. And then the measurable Riemann mapping theorem is telling us that if we have an almost complex structure with bounded dilatation, so nowhere you have to go arbitrarily far out towards infinity, you have a bound on all the dilatations, then there exists a quasi-conformal mapping which will get you back to the ordinary one, so that the field of ellipses introduced by this will be the same as your given field of ellipses almost everywhere. Everything is almost everywhere. This is a big theorem, so maybe if you don't get it right now, I'll tell you how I'm using it. So how do we apply this to the simplest surgery construction where we would not change the map, not the space, but only the complex structure? So suppose we start with something holomorphic in the ordinary sense. You have the usual multiplication by I. We are seeing these field of circles everywhere and nothing strange. Then suppose we have an almost complex structure which is F invariant. So what does that mean? It means that wherever you can form the differential, this will take the ellipse, maybe not to the ellipse at the image point, but up to scaling. Because, I mean, two similar ellipses account for the same complex structure. So you're not really paying attention to the scaling, but just how the ellipse is placed. So if we now have F, and we know that it is satisfying this relation, then we can apply the theorem. We have an almost complex structure, so we know that there is such a quasi-conformal map, phi. So we can form a new map. So we say, okay, this is our new map. So what will it do in the points where you can form derivatives? It will go from a circle, phi inverse, it will go to an ellipse. Then by F, it will go to an ellipse at a different point. And by phi, it will take you back to a circle. So from this strange thing, you are getting back to a holomorphic map. I'll have to say almost everywhere, but then there is a wonderful lemma called Weil's lemma, which tells you that's enough. To say that it's taking circles to circles almost everywhere, it will have to be holomorphic in the ordinary sense. Okay. So I go back to this example again and say I'll use it in a different way. So you start by a polynomial. In a clever way, you change the complex structure so that it's invariant under the given polynomial. So I mean, it's not just anything you can think of. You kind of know what you are looking for. But so there is a way to change it so that ellipses here goes to ellipses here. So it's invariant under the polynomial. And then we apply the measurable Riemann mapping theorem, and we get a holomorphic map. And since this was a quadratic polynomial, and this is defined in all of the plane, and it's now referring to the standard complex structure, it's again a quadratic polynomial. And then it just turns out that you can choose your map such that you are going to have a polynomial in this particular form. So that's how you can move from one, maybe I should go back now. Here. You can move from any C value you have chosen here to any other C value in this component, knowing that, okay, I keep the dynamics. So just by keeping your original map, changing the complex structure, and then applying the theorem, you move around and see that inside this component, they all have the same dynamics. So it's not just that it's the Julia set being mapped to the Julia set, it's points all over the plane that are mapped, and the dynamics is kept in that sense. Then I want by telling you just the main thing of a surgery of the different kind where we're changing the space. So that may be a little bit harder. So here's the Mandelbrot set again, or the boundary of the Mandelbrot set. And there is a curve here, which is a classical curve called a cardioid. And it can be parametrized in this way, where lambda t is e to the 2 pi I t for any t in the unit interval. And then there is this formula. So if you let t run in this interval, you're really parametrizing that cardioid. And I've just marked whenever you have a rational value of t, I've marked a few rational points. Here's 1/4, here's 1/3, here's 1/2, here's 2/3, 3/4. It turns out that the Mandelbrot set is the closure of what's inside the cardioid, I mean together with the cardioid then, together with something attached at every rational point. So we can name what's attached, and that's called the P over Q limb. So everything you see here to the left, that's called the 1/2 limb. Everything you see up here is called the 1/3 limb, and here the 1/4 limb, etc. So the next surgery I want to explain is that we start by any C value in the 1/2 limb. So any, any C value out here. And for the illustration, I've first picked this one and then that one. Anyway, so I'm here. And the curves surrounding the fractal here are defined by a potential outside the Julia set. So they are equipotential curves. So just accept that there are some simple closed curves surrounding and coming closer and closer to the Julia set. And the red curves I've drawn by hand, they are orthogonal trajectories to those. And they can all be named by how they come asymptotically to the angle they come asymptotically to at infinity. So for every point in this 1/2 limb, there are two curves always named by the argument or angle 1/3 and 2/3 that land on this point, and that is a fixed point. That's just a characterization of what you see in the 1/2 limb. So what we do in this other surgery is that we take away the part to the left. We just cut it off. And then we have to glue together that curve with that curve. And how do we do it? You glue a point of some potential to the point with the same potential. So I hope you can imagine how you close it. And then we have changed the space, so we have to change the map. And what's very common in dynamical system is if you do such a thing is you say, I take the first return map. Meaning that, say, for instance, if you take a point in here, I should point up here. If you take a point in here between the two red curves, one iteration would take you to the left over here. And one more iteration will take it to the rest. So when you do it down here, you say, oh, I enter a forbidden part of the space, so I have to iterate further, and then you come back. So that's why I say, here we have to take the second iterate to come back to the allowed space. Here we have to take just once the polynomial because we are moving in. So then you will see that we have created some lines of discontinuity because on one side we take the polynomial once and on the other side we take it twice. So we have to repair the map to smoothen it, to make it continuous, and locally we make it quasi-conformal. Okay, then there is a lot of things of technicalities how to do that. But at the end we can define an almost complex structure so that this is invariant under the new map. Not the first return map, but the one where we have no discontinuity anymore. And then we apply this measurable Riemann mapping theorem. And again, we get a holomorphic map, and this time it became a cubic polynomial. So what we really did here is that we created a new critical point. That's this one. This point up here is mapped to the fixed point, and then it's staying there. So, of course, it's doing the same thing here. It's mapped here from the right-hand side by one iteration, staying there. Under the other one, by two, it's still staying there. And it's so that if you look at a half circle here, it gets you into a half circle here. If you look at a half circle on the other side, it first maps you here to a half circle and then goes back. So maybe that's too much in the head. So here, that's what I've cut away. I'm looking at this point, saying that if I take this curve, it will map to here. If I look at this curve, it is first going over here, and after the second iterate, it's going there. And then you should see that it's closing. So we go around that point twice. So we have created a critical point here. And it has a special dynamical behavior because it's mapped to a fixed point in one move, and it's staying there. And then the old critical point 0 up here, that is here, it's still a critical point. So we have a cubic polynomial. So what we were able to obtain, so that's a result I have together with Duadi, was to obtain that all of this in the Mandelbrot set, the 1/2 limb, was mapped to a thing which is homeomorphic, but in a one-dimensional slice of cubic polynomials. Of a special behavior, one critical point is prefixed, and one can say more. So we obtained a result in parameter space. And then here you see another example. It's just starting from a different quadratic polynomial in C in the 1/2 limb, and you do the surgery and you get a cubic polynomial. You cut it away, this part. And then it gets distorted, but it's otherwise similar. So what we learned was, we learned a lot about the cubic polynomial, the dynamics. Although they seem different, we have an understanding of that they are similar in some sense. And that theorem I generalized together with Nuea Fagea. We met at summer school I organized in Denmark in 93 when she was a graduate student, and she was looking at polynomials of higher and higher degree where q was tending to infinity, because she was really interested in maps lambda set e to the set. And since there were more knowledge about iterating polynomials, that was kind of a natural way to say, how can we understand parameter space gradually going towards q to infinity? And when I saw her picture, I said, I think I know how to explain that. So so we were then looking at this family, and for increasing q, we could draw the drawing similar to the Mandelbrot set. So they always have the unit circle in here. You can't see that exactly, but there is always a unit circle, and then there is a limb, which we call the zero limb, because it's always attached to the point with zero argument. So this point is 1. So everything here, we could prove that now the 1/3 limb of the Mandelbrot set is homeomorphic to what we see here. The 1/5 limb of the Mandelbrot set is homeomorphic to what we see here. And the technique was kind of the same. We were cutting away, we were forgetting some of the dynamics, we were just being able to compare all kinds of limbs with structures here. So I'm going to tell you, no, it's up here. The theorem is up here. So we obtained a homeomorphism for each P over Q coprime, where the P over Q limb is mapped to the zero limb of Q. So you will see at the right hand that the P is gone. So no matter which limb with the same denominator we looked at, we were comparing it to the same thing. So it's really, we have a lot of things in the Mandelbrot set. We know that they are just the same. They look very different. The dynamics look different, but we have an underlying space where we understand how they are related. So this is my last slide. Just to say, when you go further up with Q, it looks very, in the Mandelbrot set, very curly and so on. In this other family, it's all stretched out, more and more going off to infinity. And what is remarkable is that you see there is a line of symmetry. So everything here is symmetric around the real axis. So in here, although it's not so visible, there's also a line of symmetry. And there's one thing remarkable about the Mandelbrot set, that we know it's connected, but we don't know still if it's what's called locally connected. We don't know if around every point that there is sufficiently small local neighborhoods. That's still an open question. If it was known to be locally connected, then there would be an easy consequence that it's also pathwise connected. So we still don't know if the Mandelbrot set is everywhere pathwise connected, that you can connect any 2 points in there by a curve. So all of part of the motivation, not really for this one, but for other part of work, is that, I mean, here it's kind of easy to prove that in this set there is a whole interval along the real axis which is really inside the set. So for the same reason, we know that there is a curve over here which is really a curve connecting points, and so the line of symmetry or arc of symmetry over here is a topological arc, as we would say. I mean, it's really a curve. So hidden, I would say, a lot of the technicalities. And that's really what is making work hard for us, is to explain all of this, so to go deep into the tools and why it works and why we have these different kinds of surgery. But it's really a lot of fun, and I think part of the reason why I'm still so fascinated about it is it's combining more or less everything I've ever heard about in mathematics, and I still have to look up new things. It's very geometrical. I'm very motivated by geometrical structures, so I know what I have to think about. I'm not really an analysis person, but I have to be. And I'm willing to go through the hard analysis if I have to. Before coming here, I was reading a paper by a Swedish female mathematician dividing things up, saying there are hard subjects like mathematics and physics, there are few women. There are harder subjects in mathematics, perhaps, where there are fewer women. And I thought, okay. And then she got me. She said there are hard analysis and there's soft analysis, and there are fewer women in hard analysis. So I don't know anything about all these statistics, but I mean, I seem to fall into the softer place. Now, the Japanese women have left. Is that true? So I have been very touched by the conversations I've had with many of you, not that many, but yesterday night the Japanese women talked to me and said they would like to give me a leaflet because they were thinking of making a network for women in Japan. So Takako Hashimoto, she left clearly, and she gave me a leaflet, and I really liked it very much. So the title is 7 Practices of Working Mother Researchers. And she says, consider woman life as an optimization problem. I think that is good. And I just want to say 2 of the last 7 points she has. Show a commitment in the work. I think that's important. Be a little more flexible and challenging with confidence, and that's important. So looking back at my long life, where I have family and 2 children, it has been worth everything. I mean, I have done many other things than mathematics, but I'm still enjoying when I have a period of time, like a week, where I do absolutely nothing else except eating and sleeping and so on, because this way of concentration is something. The way I solved my family life when the children were small was to share a house with one of my mathematical colleagues, and we had children almost the same age. So we were 4 adult people in the house and 4 children, and for about 7 years I arranged that I had a day without teaching in my department. So I would be home that day, cook for 8 people and shop and wash clothes and take care of the children. And then on Saturday I was going to the department to work in peace. And my husband could not do that, but he was doing the shopping and weekends. And it worked just perfectly. So that was the solution for me. So as you say, everybody has to find their way. So certainly I've been very satisfied as a mathematician and with doing many other things. So thank you. Yeah.
May I ask a rather probably quite stupid question? It's on an earlier slide where you have your 4 Julia sets and your 3 transformations.
How far back?
In fact,
More?
yeah, there. I'm sure this is a stupid question, but I would just really like to
No.
know. When you're doing this
Yeah.
transformation, are two of the points which are close together on top left still close together on the top right, or are they far apart?
So this drawing is meant to be exactly the same as this one.
But when you're doing your
Okay, I understand.
you are operating on this set.
So I'm saying if I take a point here
Yeah.
and I map it, now I have to think what I do. No, I take a point, say here, then I map it into here once. So by the polynomial starting here, my image would be over here.
So if you've got your point in the first image,
Yeah.
and it lands in the second image, but not in the same place.
Oh yeah, no, it's moving by the polynomial. I mean, it's
not-
absolutely
it's
moving.
not landing in the same place.
No.
So if they're too close together in the first image, are they still close together in the second image, or are they in different parts?
So what should I say? If I start in one of these white things, take two different points in here,
Yeah,
they will be two different points in here, and in that sense close together.
they're always so close together.
I mean, it's really, with the quadratic polynomial, it's rather simple in the sense that, as I said for the other thing, if you take the Julia set away from the plane, it falls into infinitely many connected components. And a whole component here is mapped to a whole component. So close points in one will be mapped to close points here. And the dynamics is kind of stable. They will keep following around. So that's not completely true if you are on the boundary.
This is what I was really thinking about. Was
Yeah,
the boundary.
that's,
Yes.
then it's chaotic.
So when you're mapping with the Mandelbrot set, then it's kind of disintegrating, but reforming in a different.
Yeah, so
That's
so here, if say that you take two very close points, I mean on the boundary, in the Julia set, and you continue to iterate for some time, maybe long time, they will stay close, but suddenly they will be almost opposite, I mean. And most often, of the point you pick, an orbit will just be dense in the Julia set. There are periodic orbits also, but the most general dynamic situation is that the orbit will be dense. You're just all over. I don't know if I've answered your
Thank you so
question.
much. Sorry. Obvious.
More questions? Fatal again.